All right, we're going to look at range today. Now, range is a very specific term. It's a term that we use to describe the distance from where something was launched from to where it lands if it's fired over level ground. And so we're going to be doing an angled launch problem with the initial and the final heights the same. So there's a lot of problem types here. So let's go ahead and identify those problem types and then solve this problem to figure out what that range is. So clearly, the first thing is it's moving in both the x and y directions. So I have a 2D motion problem, so I list both my x and y directions, and I'm sure to add those little components. We don't want to have two a's that are the same, okay? So we want to make sure we have those little x's and y's on there to differentiate between the x and y directions. And again, we don't have them on time because our time is the same for these two. Okay. So that is a common variable between them. All right. So what else do we have for a problem type? Well, it's moving in the x direction and only under the influence of gravity. So free fall in the y. So that means it's projectile motion. So as soon as I can identify something as moving in the x, free fall in the y, I know it's projectile motion, meaning my acceleration in the x direction is 0 meters per second squared, and my acceleration in the y is negative 9.8 meters per second squared here on Earth. If the acceleration is 0 in the x, these two velocities are going to be the same. And if my acceleration is 0, I'm also using equation number 2 in the x direction. So x equals x naught plus v naught xt plus 1/2 axt squared, but that is 0. Okay. So moving along, it's not launched horizontally. This one is actually launched at an angle. And whenever we have an angled launch, we have to go ahead and resolve that initial velocity, that 20 meters per second in this case, into components. And it was fired at 25 degrees. You can imagine this being like a soccer ball kicked or something along those lines. And so we do have to resolve it into these components because the 20 meters per second is both in the x and the y. So we got to figure out what portion it goes in our x direction, what portion goes in our y direction. So I have 20 cosine of 25 here, and I have 20 sine of 25 here. Put that into our equation, so I have 20 cosine of 25, and I have 20 sine of 25. So it's an angle launch problem. We are trying to find the range, so we're not going to be dealing with the max height, so it's not a max height problem, but it is an initial height equals the final height, a y naught equals y problem because it starts and ends at the same height. So that does do a few things for us. One of them is that we find out that these two values are both going to be 0 because it starts and ends at the same height. And we find out that the final vertical velocity is the opposite of the initial, so negative 20 sine 25. Okay. So we have gone ahead and we've set this up. So now, where is the range? Okay, so what other information can I maybe fill in? Well, I'm going to say it starts at x equals 0 here, and I'm trying to find the range there. All right, so I'm trying to find x. Okay, I've got all my problem types identified. The rest is just solving the problem. So this is 0. So in order to find x, I have 20 cosine 25 times t. I don't know what t is. So what can I do? Well, I know it's the same in the y direction. So what I'm going to do is I'm going to go ahead and solve the y direction for time. So what equation is going to work well for me here? So there's two ways you can do this. If you caught that y naught equals y and you got that negative here, you can go ahead and use equation 1. You can say that v equals v naught plus at. And this is all in the y direction. So you can go ahead and use that one. Or if you didn't catch that, and I'll show that one now, if you forgot about that, you can go ahead and use equation number 2 because you don't have v final. Okay. Now equation 2, another benefit to using that is, what if it isn't a y naught equals y problem? Okay. If it's not a y naught equals y problem, you're going to be using equation 2 with time anyway. So let's go ahead and use that one. So I have y equals y naught plus v naught yt plus 1/2 ayt squared. Now, you might look at this and you see t squared, t, and no t. Oh, I got a quadratic. And yes, if it doesn't start and end at the same height, it will be a quadratic. But in this case, because these are both 0, our quadratic doesn't work out that way. So I can factor out a t, so I have v naught y plus 1/2 ayt all times t. So what solution for time is there? There's a t equals 0. And yes, it is at that height at t equals 0. But is that the time we're concerned about? No, we are concerned about this time over here. So that's the time solving for in here. So I'm going to move that v naught y over. So I have negative v naught y equals 1/2 ayt squared. Okay. So again, I'm solving for the solution for time in there. And I just need to, oops, that's not t squared, that's just t. Go ahead and multiply by 2, divide by ay. So I have negative 2 v naught y divided by ay equals t. Plug in my information here, and I have negative 2 times 20 sine 25 divided by negative 9.8 equals t. Okay. Now another way I could write this in more of a general form would be negative 2 times the initial velocity sine of the angle divided by negative g. And you'll see that those negatives cancel out. Now the reason I'm writing it in that generic form is there's something called the range equation, and it's kind of a nifty little equation here. And so if I bring that time over and plug it in, I'll get a number for x, okay? So I will get an x value if I solve for time here, plug it in, and plug it in here. So if you're following along with the calculations, you should get 31.3 meters. Again, make sure your calculator is in degree mode. Now, what if I want to do it more of the generic way? I want to do that range equation you're talking about. So the range equation works out like this. R is our x, we're going to call it range, is equal to 20, my initial velocity, times the cosine of the angle, times t, which is 2 times v naught sine theta divided by g. Okay, so I'm going to go ahead and I see a v naught times a v naught, so that'll be v naught squared. And some of you out there just math it up a lot. So you see 2 sine theta cosine theta. Oh, and you are just thinking angle identities. You're getting all excited. And you're like, oh, that's a double angle identity. That is the sine of 2 theta. Yes, it is. So we can make that. And so we end up with this equation that you'll see from time to time to describing the range something can travel as the initial velocity squared times the sine of twice the launch angle divided by g. And this has some criteria. It only works if you're on Earth and if you start and end at the same height. So you usually got to fire this thing over flat ground in order for that range equation to work. Okay, but this is how you can find range.